A uniform elastic string lies on a smooth horizontal table, and one end of the string is attached to a fixed peg. So you have this peg, and one end of the string is attached to that. And the other end is being pulled at a constant speed u. So if we just, if we look at this end, okay. So this end is being pulled at a constant speed u, this point here. And at time t equals 0, the string is taut with length a. And so this length is a at t equals 0. Now you want an expression at time t of the point on the string which is at distance x from the peg at time t. So this distance x is at a time t. So meanwhile, has everyone read the question? Try to think about it for some time and see if you can look at the relation. I think I'll just go with the Zoom whiteboard. That's all right. But that means you'll not be able to look at the question at the same time.
So, maybe I can send the question in the chat.
Yeah, that'll be nice. Thank you.
Try.
So, yeah, you have this peg and an elastic string, and you know that this point is moving at a speed u, right? And you know that initial length. So if we assume there is an axis placed here, if there's a scale placed here with a 0 on the peg, then you know that initial position of endpoint. So let's call this endpoint P. So is A. It's at the mark at A, at t is equal to 0. And then you're told that it starts moving with a uniform speed u. So naturally at time t, point P is at, could anyone in the chat type the answer? So at time t, the point P is at coordinate. Yeah, is it ut? So you know it's initially at a, exactly. So it's u plus a plus ut. So this is the coordinate of the point at time t. And now you're asked the speed of the point. So you have some point here, let's call it q, and you're told that q is at a distance x, right? So at time t, so at time t, q is at this distance, and now you're asked what's the speed of q. So let's see how we can look at this. The key point we have to look at is the fact that the string is uniform. So the uniformity is important here in that we know that the stretching throughout the string will be proportional to the length from the endpoint. So if this point is at a distance a plus ut and is being stretched at point u, then this point will be stretched at a speed proportional to the ratio of distances. So you know that speed of q over speed of p is equal to coordinate of q over coordinate of p. And so you're just supposed to find this. So let's say the variable is v, and speed of p is u, as we know, it's constant. This is equal to coordinate of q at time t is given to be x. And coordinate of p, as we found out, is a plus ut. So now you know that, let's call this V naught. V naught is x upon a plus ut. And this is a solution to the first part. The key factor you had to remember was the fact that the string is uniform. And so the speed at which every point moves is proportional to the lengths. So
Plus, I think there's a lack of u because it is xu over.
Yeah, sorry. The xu over a plus ut. Thank you. Right, so let's look at the next part of the question, which is, how do I look at it now? Yeah. So the next part of the question says, an ant wants to walk along the string starting at t equals 0 at the peg. The ant walks at a constant speed v along the string. Then at time t, the ant is at a distance x from the peg. Write down a first order differential equation for x. So there's a bunch of things here. Let's say the position of the ant at time t is given by the variable x. Then we know that, could anyone write in the chat what the speed of the ant would be at any time, just in terms of x, from what you know about how speed and distance are related? So you know that the position is x. So distance from the starting peg is x. And now you want to find out the speed with respect to the starting point. So someone says x over t. That's not entirely accurate. And why is that the case? So could someone just define speed? So yes, it's the derivative of x with respect to time. So speed is defined as rate of change of distance. So the rate of change here is important. So you know that the speed of the ant is dx over dt. It's not x over t because it would be x over t if the speed was uniform, but it's not uniform, as we'll find out soon. And the instantaneous speed, so I should have been more specific and called it the instantaneous speed, in which case it would be dx over dt. And now we know a couple of things about this. We know that the instantaneous speed is, suppose this is the peg and this is the string, and the ant is at some point here. The ant is at a distance x, as we defined. Then in the ant's perspective, the ant is moving at a speed v with respect to the elastic. So the best way to imagine this is, think you're walking on a treadmill. Then your speed is equal to your speed on the treadmill plus the speed of the treadmill itself, right? So with respect to the peg, the ant has two velocities. Firstly, the point itself was moving, as we found out, because this end was being stretched. So this point was going at a speed of ux over a plus ut. And on top of that, the ant itself is adding a velocity v here. Does everyone follow that? So now what we know is speed of the ant is this thing. So speed of the point itself plus whatever speed the ant has with respect to the elastic. And this is the differential equation that the ant is following. It's a first order differential equation because the derivative has degree 1. It's just the first derivative of x. The important thing to realize was relative velocities. And that's a concept I assume all of you have learned in mechanics. So if you have two objects, if you have two people, A and B, and A is moving with a velocity VA, and B is moving with a velocity VB with respect to the ground, then in what A sees is B moving with the velocity VB minus VA. So the relative velocity of B with respect to A is VB minus VA. And we use the same concept here. So one of the observers is the point on the elastic with respect to which the ant has velocity V. The other observer is the peg. And you want to find the velocity as observed by the peg, which turns out to be this thing, the addition of those two. In the actual exam, you don't need to explain this stuff. This is just for your reference. But in the exam, you could just say the speed of the ant is speed of the point plus speed of the ant with respect to the point, and that is equal to ux over a plus ut plus v. And this is the differential equation that the ant follows. So if everyone's followed that, could you just type a yes in the chat? If you have any doubts, feel free to type. If I'm going too fast, you can say that as well. Yes, that's fine. Thank you. Yes, so as we can see, they're fairly simple concepts that they managed to tie in together. And the first one was just knowing how proportional speeds work. And the second one was just knowing how relative velocities work. And together you found a nice differential equation for the speed of the ant. And that's the second part. Now let's look at the third one. So now what you know is, now that you have written down a first order differential equation, you're supposed to verify this particular thing. So you're supposed to verify that d by dt of x over u. So you're supposed to verify this thing. And there's two ways you can go about this. The first way is we had the nice differential equation. So I'll just write down the equation here for your reference. We found that dx over dt is v plus ux over, is there an eraser here? So this is the differential equation you have, and you want to verify this thing. And I think I messed up here as well, and it's supposed to be a plus ut and not u plus at. Yeah, so you're supposed to verify this thing. One way is just you go from here to here, which is somewhat the more complicated way. And I would not recommend doing that in an exam. The simplest way is to look at this and try to show this is true. And that's why they said verify this. So let's look at the LHS and try to get to the RHS. So you know that the LHS is d by dt of x over a plus ut, right? And now you're supposed to differentiate this complicated expression. So what do you think is the next step? We know how to differentiate the ratio of two things. Have you done the differentiation, the product rule of differentiation in school? Yeah, so you've seen the product rule of differentiation. So what we have here is I just write down the quotient rule for those who don't know. So d by dt t of f over g is g df by dt minus f dg by dt over over g squared. So this is the quotient rule of differentiation. Even if you don't know this, you can get this easily from the product rule and imagining 1 over g to be a function. But that's just an aside. So let's use this quotient rule and solve and differentiate this in the simplest way. So the differentiation of, so we first have g, a plus ut, and dx by dt minus x and differentiation of a plus ut. So could someone in the chat write down what the value of this is? D by dt of a plus ut. It's u, exactly. And the denominator is just g squared, so a plus ut whole squared. And so now we know that this thing here is u, and we also know what dx by dt is from here. So let's use that as well. So we have v times, so if you multiply this by a plus ut, you get v a plus ut plus ux over a plus ut times a plus ut, that is ux, minus ux over a plus ut whole squared, right? This is just substituting dx by dt from here, and d by dt of a plus ut is u, as you pointed out. And that's exactly the right-hand side. The ux and the ux cancel out, and you're left with v over a plus ut, which is what you needed. And so you verified this equation. And I mean, it's a beautiful equation in that it's somehow telling you that if you want to find the derivative of the distance, you just need to, like, can you see the symmetry here where the a plus ut is essentially being ignored in some way, except this is the absolute distance and this is the relative distance, so not really. So this is the equation being followed. If you followed this far, just type a yes in the chat. If you have any questions, feel free to address them as well. Feel free to ask them as well. Nice, so everyone followed that. And that's the third part of the question. Again, it's a bunch of unrelated concepts that are tied together nicely in a singular question. So the third unrelated concept in some way was just differentiating a quotient of two functions. And if you could do that, you verify this identity. And that's an important skill in an exam. It's not to get disheartened by feeling that you have never done mechanics before, because this part of the question was essentially just differentiating a function. And you need to be able to isolate individual concepts in a question when you look at it. Now, the third part of the question is, the next part of the question is to actually find out the time taken by the ant to reach the end of the string. So the question reads, show that the time t taken for the ant to reach the end of the string is given by ut equals a times e to the k minus 1, where k is u over v. So now what we have is, I'll just give a refresher. There's an ant that's starting from here at t equals 0, and it's reaching this point by t equals t, t equals capital T, right? So the ant here is moving with a velocity governed by an equation. So there's two equations governing the velocity. We first show that dx by dt is v plus au over a plus ut. And the second equation that we derived from this one was d by dt of x over a plus ut is v over a plus ut. And now, using this information, we are supposed to find out a relation between, we have to find out a relation for the time capital T. So have you done integration in school? I assume you have. So the next concept is just trying to find out what happens here. And since they made us derive this equation, I think it makes the most sense to use this instead of this one, because this is a particularly nasty form to integrate. If you have tried to integrate this before, if you have tried to integrate similar functions, you would realize that this is very hard to integrate. Whereas this is readily available in terms of a differential equation in which one of the sides is a clean derivative. So let's say x over u a plus ut. Let's call it y. Then this equation says dy by dt is v over a plus ut, right? And so we can just rearrange things and put integration signs around to get dy equals v over a plus ut times dt, and then we can just put in integration signs here. And now we're supposed to solve this. And let's put limits here. So the variable here is dt, and so the time is going from t equals 0 to t equals capital T, right? And the variable here is y, the variable you're integrating over. So let's look at what y is at t equals 0. At t equals 0, y is, could someone type in the chat what y is at t equals 0? You know the ant is starting from origin. X over a, yes. But as I would like to remind you that x itself is a function of time. So you can simplify that further. You have x of 0 is equal to 0 as given in the question, because the ant started from the peg. So in fact, at t equals 0, the value of y is 0. Yeah. So this is a bit tricky, but if you follow, it's important to realize the x itself is a function of t here. And once you realize that, then you can see that y at t equals 0 is 0. And when the ant reaches the endpoint, the value of y becomes any guesses? So let's look at what the quantity y here. The quantity y is the position. So I'll just point out that x of t is not, I mean, you're supposed to find out x of t over a plus ut. This is what you're supposed to find out. So let's inspect the quantity y first. I'll go on a new screen. So y is x over a plus ut. And if you look at what's happening, this is the peg. X is the position of the ant from the start point at the given time. And a plus ut, as you would remember, is the position of the endpoint. And so x over a plus ut is in fact the ratio of how far the ant has gotten towards the end of the string. So if you observe this, then it's very easy to see that y at t equals 0 is actually 0 because the ant has not covered any distance, and y at t equals t must be equal to 1 because the ratio of distance covered over the distance needed over the total length of the string is equal to 1, because when the ant reaches the end, it has covered the entire distance. So y is going from 0 to 1. And this was somewhat a tricky observation, but if you manage to do it, then the rest of the question is just an integration problem that you can solve. So does everyone follow this logic? The key idea was isolating the quantity y, because you can see d by dt of this thing is, and that's somewhat easy to integrate. Just type a yes in the chat if you have followed, and if you have any questions, please ask, because this is not a simple problem. Nice. People seem to have followed it, the logic. And then what's the integration of the left-hand side? Is the integration of dy from 0 to 1. So you can imagine this as integration of 1 dy from 0 to 1. And the answer is, could someone in the chat point it out? So you want the integration of 1 dy from 0 to 1. Let's look at this quantity. So 1 can be imagined as, so the integration of 1 is y, and then you're just supposed to put the limits from 0 to 1. Because 1 can be imagined as x to the, as y to the 0, and then you can just use the formula y to the 0 plus 1 over 0 plus 1, if that's how you prefer to do it. And so it becomes y, and then you're supposed to integrate it from 0 to 1. And in that way, the left-hand side evaluates to 1. So this is fairly standard integration that if you've not learned yet, you will by the end of your A levels. And so by the time you do STEP, you'll be very comfortable with doing integrals like this. And now this side is slightly tougher to integrate. Let's try to integrate this on the next page. So we're supposed to integrate, the quantity is v over a plus ut. And this is somewhat, and we are supposed to integrate with respect to t. So firstly, let's observe that v is a constant, so let's pull it out. So it's v integral of 1 over a plus ut dt. And have you done integrations by substitution before? Type a yes in the chat if you've seen integration by substitution. No if you've not. You've seen integration by substitution, right? So let's try to substitute something. So let's say a plus ut equals some nice variable z. Then now you're supposed to also find out dt in terms of dz when you do this. So then you see that u dt equals dz. So dt is equal to dz upon u. This is an important step that people always forget, that when you're substituting for this part, you're also supposed to change the variable you're integrating with respect to. And now we're integrating with respect to z instead of t. So we also have to switch the dt to a dz. So once we do the substitution, this becomes v integration of 1 over z, because a plus ut was z, and then dt was dz over u. So 1 over u dz. And now we know that the u is a constant as well, so we can pull that out as well. So it's v over u integration of 1 over z dz. Right? And yeah, so the question tells us that, actually, let's forget about that. So we have v over u, integration of 1 over z. What is the integration of 1 over z? Someone in the chat. Yes, it's ln z. It's ln z, right? So now this is the integration you have. And let's not forget our limits. So the limits were from 0 to t, 0 to t. And since our t is going from 0 to t, our z is going from a to, z is going from a to a plus u capital T, right? And the same limit here. And the limit here. So I'll write that on a new page. So the integration came out to be v over u ln z from a to a plus u capital T. And now it's just about substituting the values in. So v over u, upper limit ln a plus ut minus lower limit ln a. And can we simplify this further? Someone in the chat? Is this the simplest form it can be in, or can it be simpler? Yes, so as Anisa pointed out, we can, the difference of two logarithms is also the ratio of their arguments. So you have something like v over u ln a plus ut over a. And I think this is the simplest form it can be in. I mean, you can also cancel out the a's here and 1 plus ut over a, but let's leave it this way. So now we have found out what the right-hand side of the equation is. So now we know that the left-hand side of the equation was 1. I'll bring up the equation just for you to look at once. Yeah, so this thing was 1. And this side, as we found out, was v over u ln a plus ut over a, right? And now it's just a matter of simplifying this further. So we found out that 1 is v over u ln 1 plus ut over a. This is just dividing by a through. Is this all right? And so ln of 1 plus ut over a is u over v. And the question tells us that u over v should be written as k. That's just a new variable that called this. So now you know that ln of this thing is k. And what's the next step in the chat? Exponentiate both the sides, right? So 1 plus ut over a, if you exponentiate ln, it's essentially just bringing out the argument. That's equal to e to the k. And then it's just a matter of rearranging, and you get what you needed. It's a e to the k minus 1. And we're done. That's exactly what we needed to find out. And we have found out a relation for capital T, which is the time it takes for the ant to reach from the start point to the end point. And it's not as, it's an exponential term, because this end point is also getting further from the ant as the ant is walking. So there's a bunch of factors at play here. The point at which the ant is speeding up, and the ant itself is moving at a constant speed with respect to the elastic. And in the end, it all comes out to be in this beautiful differential equation that has this exponential solution. Did everyone follow this? Yes in the chat if you did. And please ask questions, because this is a fairly hard question. And it's important that you clear all your doubts. Nice, all of you followed that. 2 of you followed that. I'll assume most people did. So nice, yes, people did follow it. And let's, so now the next part is, it's a one-line question which says, on reaching the end of the string, the ant turns around and walks back to the peg. And then you're supposed to find in terms of t and k, the time taken for the journey back. So now the ant has reached here. At some time capital T. So you have a plus u capital T. The ant has reached here and it decided to go back with the same speed, v. So now we're supposed to find out the time for the return journey. Now let's think about this. There's a couple of ways you can go around this. The first way is just to solve the whole thing again, which is probably a mess. And you don't have the time in the exam to solve the whole thing again. But we have a lot more information now. We know the time it takes to cover the journey one way. And then it's a matter of observing that the situation is somewhat symmetrical, except the ant is starting from this endpoint and it has to reach the start point. So let's do a small trick here. Let's use a small trick and assume that this is the origin now. Let's assume that the endpoint is the origin. And then what ends up happening is the peg is moving with respect to this point. Suppose you have fixed an I on this endpoint of the string. Then with respect to this I, the peg is moving with a velocity u, and the ant is starting from 0 and moving with a velocity v with respect to the string. So this does not change with respect to the I, because this v was with respect to the string in the first place. It was never with respect to the peg, nor with respect to the other endpoint. So now with respect to this I, which is fixed to the endpoint, the peg is moving with a velocity u, and the ant is moving from here to here with a velocity v, with respect to the string. And can everyone see how this is exactly the same problem as before, except the initial length has been changed from a to a plus ut? That's a slight, it'll take time to sink in. Think about it for a couple of minutes. But that's exactly the same problem if you change the frame of reference from the peg to the other endpoint. And in an exam, you would be expected to explain this in a couple of lines, the reasoning. So you're switching frame. So you're switching the frame of reference to endpoint, and then you observe that the problem reduces to a problem you've previously solved. So there's a common joke around this, which is a mathematician and a physicist were given fire training. And the first time the physicist's bed is set on fire, the physicist manages to extinguish the fire. Then the physicist's dustbin is set on fire, and the physicist does the same procedure. He takes the bin and he takes the extinguisher and sets off the fire, puts off the fire in the bin. And now it's the mathematician's turn. So first the mathematician's bed is set on fire, and the mathematician does the procedure. He takes an extinguisher and puts out the fire on the bed. And then as a second test, the mathematician's bin is set on fire. And what the mathematician does is he takes the fire and puts it on the bed and says, now we've reduced it to a previously solved case, hence done. That's exactly what we did here. We first solved a complicated problem, and now we're supposed to solve the return case. We reduced it to a previously solved case. And now the solution is simple. So in the first case, the answer was, let's see what, it was ut equals a e to the k minus 1. And now we're supposed to find out the time t1, which is the time to return. So using the same equation, you know that ut1 will be equal to the initial length. Initial length is a plus ut. And k, as we would remember, is u over v, which is same in both the problems. So it's e to the k minus 1 again. And that's the other answer. That's the time it takes to return from this point to this point. Did everyone follow that logic? And maybe type a haha in the chat if you appreciated the joke. But we've solved a step question. And that was the end of it. The last part is, in some sense, the nicest part of the question, in my opinion, where it just takes a clever observation to see that it is the same problem, and you don't have to go around solving it again. The other way you could probably do it was consider how the velocity v is just shifted to negative v in the second case. And that would, I think, be a similar solution. But I encourage you to try out other solutions to the second part in your own time. So, Ursula, do we have time for one more question, or are we done?
Right. I think there's about 5 minutes.
5 minutes left.
If you want to show what a possible next question is and just give them a hint on how to start, I'm sure everybody will be keen to continue by themselves afterwards then.
Okay, so let's look at, we'll be doing question 6 on the same paper of step. So 2018 step 2. And the question, if I remember correctly, goes something like, find all integers n for which n factorial plus 5 is prime. And that's the first part of the question, which is, I think it's the easy half of the question. So you're supposed to find out all integers n for which n factorial plus 5 is prime. And instead of going through a solution, I'll just point out how definitions are important when doing maths. And this is a skill you should develop even when doing maths further in life. Is a simple mathematical statement is a condensed form of information. And there's a lot of information packed in just these 5 words, because there's a factorial here, which itself contains a huge definition. N factorial equals n times n minus 1 times up till 1. And prime is only divisors are 1 and itself. And divisors are just numbers that divide the thing. And now you're supposed to find out all integers n for which n factorial plus 5 is prime. And so this essentially says that all integers n for which n factorial plus 5 has no other divisors. Does anyone have any ideas as to what the first step would be, or any observations? Right. Does anyone want to type any observations in the chat? If not, I'll just give a hint. It's to do with the definition of a factorial and how divisors interact with sums of numbers. So there's this nice lemma which says, if d divides the sum of 2 numbers, and if d divides one of the numbers, then d divides the other number as well. So this is an important fact that will help you solve the question. Yes, so as Sasha pointed out, if n is greater than 5, then 5 divides this part trivially, and 5 also divides this part because n is greater than 5. So you will eventually hit a 5 here. And so 5 will divide n factorial plus 5. And so if n is greater than 5, this can never be a prime. And now you're just left with, so there should be a positive here. Yeah, and now you're just left with 4 cases to solve. You're just supposed to consider 1, 2, 3, and 4. And these I think you can do explicitly because the factorials are small. So n factorial plus 5 is 6, 8, 11, and what's 4 factorial? 24 plus 5, 29. So the two numbers turn out to be 3 and 4. Be a bit more clean in your solutions. Cleaner than me. I'm not used to Zoom whiteboards, sorry about that. So yeah, the numbers turn out to be 3 and 4, for which n factorial plus 5 is a prime. And the next part of the question is somewhat similar. I'll have to look. In the next part of the question, you have two theorems, which are just results you have been given. And you're supposed to find all pairs of positive integers n comma m that satisfy this weird identity. So I think the first part is nice here because it puts you in the mindset of taking two cases, n greater than 5 and n less than equal to 4. And that's essentially the purpose of the first part in this question. It's to put you in the mindset of splitting your cases. And then if you look at the second part, the theorem 1 applies exclusively for n greater than equal to 7. So a natural thing to try after doing the first part should be to split into two cases for the second part, n greater than equal to 7 and n less than equal to 6. And once you do the split, it's just a matter of using the theorems correctly to show how each case works out. So that's another thing you should keep in mind. So when you're doing step questions, especially for the pure maths ones, the first part is supposed to be easy, but it's supposed to give you a hint on how to approach the next part. So if you could make this observation, this is like the equivalent of theorem 1 for the first part. And theorem 1 for second part is for n greater than 7. So that's a neat thing to remember. Every time you're solving a question, remember what you've done in the previous parts, because there's a good chance the parts were written on purpose so that you are in the right mindset when solving the next question. I think we don't have more time, so I won't really go into the solution for the next part, but I encourage you to try it out once you go back home. You are at home once the session is over. And it will work out very similarly to the first part, once you've observed how to make the split. Thank you.